All right, well, I will get started if I can find my phone here. So scripture for today is John 16:33. Here's how it goes. These things I have spoken to you, so that in me you may have peace. In the world you will have tribulation, but take courage. I have overcome the world. It's John 16, verse 33. I'll begin with a word of prayer. Heavenly Father, we thank you again for your creation and for our ability to study it, and just pray that you guide our steps today. Help us to just understand a little bit more about physics together, Lord. In your name I pray, Lord Jesus. Amen. So for problem 31 in the mission, I want two things. Number one, I want an x versus u plot. But number two, I want an x versus velocity plot, like we did in class. So I've just said energy diagram there, which is kind of ambiguous. So let me be clear. I do want you to do both the potential energy plot and then under it the, position velocity plot. Here is a picture, a kind of a middle ground. You could think about if I had a potential energy that looked like this, if you're at a potential well, you got a critical point here, right? To the right of the critical point, you're decreasing, increasing. To the left, you're decreasing. So here you'd have du dx is negative, here you'd have du dx positive. It stands to reason then that the force pushes in the directions pictured because the force is minus du dx, right? So when du dx is positive, the force is negative in the sense it points left. When du dx is negative, the force is positive in the sense it points right. So you have the stabilizing effect of the conservative force keeping the motion close to the stable equilibrium, whereas at this kind of thing, the force has the tendency to push away a particle that's close to that critical point. But you can also see this from the velocity/position graph we looked at, where if you look at the critical points, a stable critical point will have orbits which are bound. In other words, the orbit around in the xv plane, it doesn't stray far away from the origin. Whereas in unbound orbit, an unstable equilibrium, you'll have unbounded orbits. Trajectories that go through the critical point and yet allow motion which just keeps going and going way off. We saw that if you go back and look at that example. So there's kind of two slightly different ways of looking at stability, either by direct analysis of the force and the way the force pushes on the particle near a critical point for the potential energy, or in view of the phase plane, the Poincare plane kind of plot. I should talk about power. Let's talk about power. So let us, for the sake of discussion here, suppose that you have a physical trajectory. It starts at some point r naught, and then the end point is r of t. All right. So here's some, physical trajectory of some particle. All right. And then you can ask, what's the work done as a function of time? All right. What's the work done as a function of time by some force? So the work as a function of time would be what? It would be the integral along c of f dot dr. This would be the work done by the force r. Now, specifically, that works out to the integral, say, from t naught to t of, I'm going to use the variable tau here for dummy variable of integration, r of tau dot dr d tau d tau. So I'm using tau to distinguish from t because t is the fixed but arbitrary time that our trajectory ends on. And of course, the trajectory here starts at time t naught. So that would be the work done by the force F from, say, time t naught to time t. All right? Power is, by definition, the rate at which work is done by a force. So dw dt is the power. This is equal to the power, or power, if you're a certain actor. Sorry, I'm an idiot. But you already knew that. Let's see here. So, come on. I was going to do the top hat thing. I know you guys are like, come on, computer. Wake up. So if you look at the formula behind me, if you can, see it through my computer. That might help. What happens if we differentiate this formula here? How's that go? d dt of the integral from t naught to t of f of r of tau dotted with dr d tau? D tau. How's that work out?
Would it just be f of r tau times, or dot dr d tau?
So you say f of r of something dotted with dr d something. Help me out. What's the something there? T. It's t. Tau is the dummy variable of integration. It gets used up in the integration process. The fundamental theorem of calculus part 1 says when we differentiate an integral with variable bounds, what we get is just the integrand back again, evaluated at time t. Uh-oh. How is my computer rebooted? Every time my computer reboots, the Microsoft Teams virus appears. It's one of the most nefarious viruses on any computer. It's very.
Microsoft Antivirus Defender can't defend you?
That's right. Microsoft Antivirus Defender is no defense against the Microsoft virus, which is pervasive.
Man, that's crazy.
I know, right?
It's like friendly fire is turned off.
The what virus? The rot. No, there is no rot virus. Where have you been? I read. I signed up for the Liberty notifications just this semester for my own amusement, and it has been very amusing. Like it's been great. I've been saying, do you want? It's been asking me, do you want to opt into emergency communications for like, I don't know, 10 years now, and I have always said no, because I just don't want to be spammed. But then I thought, it might be interesting. So earlier this semester, I said yes to it, and it has been hilarious. So anyway, T and T. There we go. Now, so this gives us the formula. The power as a function of time t is equal to the force at time t dot what? What is this? Well, this is work, but yeah, this is velocity, right? So the velocity at time t, or if you like, we could just simply write that the power is equal to the force dot the velocity. The power is the force dot the velocity. This is true even for variable forces, right? Another way to look at this, right? In retrospect, take this back up here. See what we got actually? We have the integral from t naught to t of what? P of tau d tau. See, that's nothing more than the power at time tau. That's what that is. To calculate the work done by a force, you integrate the power over time. That's what you do. Now, if the power is constant, then what's the integral? If power is constant, the integral is kind of boring. It's just power times time, right? But it doesn't have to be constant. The power can be variable. Here we go, 6131. Don't say I didn't ever do anything for you. There you go. Exciting, yes? So, so what's the power developed by a force which is perpendicular to the motion? If the force is perpendicular to the motion, force dot velocity is 0, right? Perpendicular forces do no work, right? Here, I'll show you an example I have in the notes. I'm too lazy to write this one out, so we'll just look at it together. If you guys don't mind. Well, even if you mind, I'm still doing it. Have you all recovered from your various sicknesses? No? Still sick of physics? I understand. I really don't understand. I love physics. But I say I understand so that I'll be more relatable. Did it work?
Yeah.
Yeah? All right. I'll take it. So this is lecture 16, which is deceptively labeled work, I think, was it calculus-based physics example or something? So in here, I have a few snazzy examples. Since I have this, we'll look at these together while I have this out, and we'll eventually get to the example I wanted to look at. But this one, find the work done against gravity to shovel the rectangular mess of wet leaves into a bin, which is height h above the flat ground on which the leaves lay. So I've got these leaves, and I'm shoveling them up into this composter, I guess. And the composter has height h, like the base of it. So you're shoveling it at least up to height h. And I said that it's filled uniformly. And let's see here, how do I do it? So there's my, as you can see, my very, very sophisticated picture of Mr. Top Hat shoveling. Completely realistic shovel size and proportion. Yeah. All right, so I say we cannot just use h because the leaves at y equals to d only have to be lifted a height of h minus d, right? So like, so if I'm thinking about like shoveling the leaves when it's already full up to the level d, those leaves have to be shoveled further up than the ones at the base, right? And the ones at the top, I have to shovel the furthest, right? So the amount of work it takes to shovel different leaves is different. Yeah, because they're going different distances. And so what I decided to set this up as is just to calculate the density of leaves. That's the mass per unit volume is density. And so the dV here is the area times dy. So the area times dy gives me the volume of this infinitesimal thickness slice, this sandwich, if you will, or slice of leaves, if you like. Length times width times dy is the infinitesimal volume. The mass would be the density times the volume, which in this case would be rho LW dy. It has to be lifted delta y of h minus y against gravity. Let's see here. And so my dw is the mass times gravity, which I believe here is rho L, this business right here, rho LW dy. This is mass times gravity. And then this is the distance that you're lifting, y minus h. And that's the infinitesimal amount of work it takes to lift that one slice of leaves. And then I add them up to get the total work done for the whole mess. So integration gives me that addition. I integrate from 0 to d. And that gives me this, which, so what's going to happen is we get that. So there it is. So if you have something where you have a different amount of work required for different parts in the object, then you just have to do an integral to calculate the total work done. Like you have to divide it up into appropriate slices and calculate the work for each slice. This is the same idea we used in Calculus 1 to calculate volume, right? To calculate the volume, you took your volume, you sliced it into slices, you added up the volume of each slice by integration. Same idea here, except I'm thinking about the work for each slice of leaves. All right. We'll skip over that one. Although that one might be helpful to you in some particular mastering problem. This is what I actually was after. And then I'll put this silly projector away once I'm done with this very serious example. Suppose you have a sub-basement filled with robot monkeys. An elevator, I mean, why not? An elevator with a mass of 31 kilograms connects the monkeys to the upstairs levels. When in motion, the elevator moves 0.32 meters per second upward, almost entirely without acceleration. All right, so we're going to ignore the brief startup motion. The efficiency of the elevator is 86%. If your maximum load for the elevator is 20 kilograms, then what's the minimum power rating you want for the motor? All right. So this is a power problem, all right, because like you want to think about how much power the motor is actually delivering to the elevator, right? Whatever that power is, a certain percentage of it's being wasted, right? Because the efficiency is 86%, which means 14% of the power that the motor's developing is not actually applying to the load. So here's how I did it. The mass of the elevator at maximum load is the 31 kilograms. What was the 30? Was that the motor? Was that the weight of the motor? I've forgotten. Rats. Or was that the robot monkey? What was that? Oh, that's the actual elevator. The mass of the elevator itself, right? Every elevator has to lift itself, right? Yeah, that's part of it. So if you can add 200 kilograms, that's the load. So the mass that the elevator is lifting is 231 kilograms. So why do I know that the force of the motor is mg?
Because your net acceleration is 0, so your net force is 0.
Precisely, right. So if we're near constant velocity, the acceleration 0, which means that the motor force, what's wrong with me? The motor force upward has to be equal to the gravity force downward, because that's the only forces involved here. There's no friction or anything else, right? So, yeah, that means that the motor force has to be equal to the weight. And, but we just worked out, right? The power is the motor force dot the velocity, right? And the velocity we said was 0.32 meters per second, yeah? So that gives me the power that actually is being developed by the motor at the maximum load. The power delivered is this. So 231 times 9. Oh, look. See, I was more sophisticated back when I wrote these notes. Look, it was 9.81 that semester. I'm much lazier now. I only do 9.8. So times there are changing. I was actually just reading my linear notes. I found a reference to Sonic on Ward's Road. That's a little bit, it's been a while. Yeah? You guys, was that before you were born? No, probably not before you were born, but before you were here for sure. I think it closed in like 2017. Where that car wash is on Ward's Road. There used to be an entrance to Liberty there before they built these tunnels. When I first started working here, like I never knew coming in to work if I was going to be stuck behind a train going across those tracks. And sometimes they just sit there for 40 minutes because we put an entrance to the university on a train yard. Yeah, that happened. So, but we're past that now. Anyway, so yay for tunnels. Power delivered is here, 231 times that. That gives me 725.2 watts. But the thing is, in order for the motor to deliver this much power, 14% needs to be wasted, right? So 725.2 watts has to be equal to 0.86 times the actual motor power, and then that gives me the minimum rating for such a motor I would need would be 843.3 watts. Yes?
You must have slashes.
The slashes? Slashes? Oh, parallel. So the motor force is directly in the direction of motion, so it's completely applied all to the, F dot V. Just becomes FV when V is parallel to the force. Is it good? Okay. All right. Can I put this away? I just wanted to talk to you guys at least a little bit about a specific real-world example with Robot Monkey. I don't know what Robot Monkeys has got nothing to do with this, does it? But I'm kind of disappointed. There's no robot monkeys in the actual problem. It's just, but anyway. So many of you are engineers. You care a lot about efficiency, right? Like efficiency is something you have to build into your designs. So I think it's good to look at an example where that comes into play. Anyway, I'll shut up about that. All right. Let me begin with my other examples. Let's see here. So example, I suppose that was example, I don't know what that was. Let's call this example 1. So suppose you're given a plot like this. So here we've got x, and this way we've got the force, All right? And let us suppose that this is minus 5 meters, that this is 2 meters, this is 6 meters. All right? And let's suppose that this is 2 newtons, and this down here is minus 1.5 newtons. All right? Furthermore, I will tell you this right here is minus 4 meters. This right here is 1 meter. This right here is 3 meters. This right here is, let's say, 5 meters. All right. Now I've told you everything about the shape, okay? So in your WebAssign, you're mastering physics, you probably have like a graph of a force versus position, right? And they don't have numbers because they've got like a graph and a scale. But since I'm really bad at drawing graphs on the whiteboard, I just put some numbers for you, all right? Question. Here's a question. If the velocity is equal to 3 meters per second at x equals to 0, then what's the final velocity when x is equal to 6 meters if F net equals the force pictured above? So context here, we're talking about one-dimensional motion, right? So what's the theorem we need to use here? What's the physical idea? The work done, right, is equal to the change in the kinetic energy. Right? So admittedly, we're missing some information, aren't we? Which is what?
It's going to be 1/2 for the work.
Yeah, the work energy theorem. But what I'm asking is, I've given you the values for the force and the position on the graph explicitly, right? But to actually connect to energy, we need to know what? Mass, right. So let's make the mass equal to 4 kilograms so that we don't have to deal with nasty fractions, all right? And also, maybe it's a cat. Well, I mean, there's really nothing terribly violent about this problem. Maybe it's kind of a waste of a cat. A dog?
What?
Mm.
I've had some pretty bad.
I'm uncomfortable using dogs in examples.
Yeah.
I think it could be kind of
You
insensitive.
said this wasn't violent.
What's that?
You said this wasn't violent.
I'm not sure, though.
Oh, never mind then. Never mind. Iguanas. I don't know.
So the change in kinetic energy is 1/2 mvf squared minus 1/2 mv naught squared, right? And that will be the integral. What's the work done? The integral is the work done by the force. The work done by the force is particular. We integrate from where? From 0 to 6 meters, right? And f of x dx, right? Now you're like, but you didn't give me a formula. That's true, I did not, but I gave you a graph, and you guys know integrals calculate area, right? Signed area, actually. What is the signed area? So we need to figure out what's the signed area under the position, whatchamacallit graph here. So you guys tell me, what's the area here? And we'll need to take that area, and we need to subtract the area below the axis, right? So down here, this is negative work.
Oh, that green part, I'm pretty sure is just 3.
So you've got 2 newtons times 1 meter plus 1/2 of what? 2 newtons times 1 meter. So you said that that works out to 3?
The green part.
Yeah, you're right. Cool. Yeah, I just didn't, I mean,
I can do basic math. Let's go.
yes. Let's go, indeed. 3. That seems to be the refrain of your generation at the moment. Let's go.
I aspire to be better than
You take that,
How far taking
You take that do better and you put it out in the hallway. I don't want to hear do better in my class. Let's see here. That is a phrase I don't agree with. Let's see here.
I guess the do or do not is the
Yeah, I say, oh, do or do not, no. No, okay, so then this right here, I don't know, what is that? Negative 4.5?
Yeah. You can just add the triangles to the side.
But the 1.5, okay. So you said that works out to minus 4.5 joules? Anyone else agree? If there's two people who agree, then it's for sure, yep, okay.
Yeah.
I have confirmation in the back. All right, we're good. So what's this? So we've got a net of minus 1.5. So the total work is minus 1.5 joules. What does that mean? Yeah, that means it slowed down, right? Also, it means that it's possible that, I don't know, this may be unphysical. Right? It could be unphysical. Think about it, right? Because if I did 2 negative work and I don't have enough kinetic energy to start with, it might be impossible. You know what I mean? Like I can't have a negative. I can't. All right. So like, for example, hypothetically, suppose I said it started at rest. Right? If I said that the motion started at rest, we'd be in trouble right now because we'd have 1/2 mvf squared is equal to minus 1.5. That's impossible because this is positive.
Just say no.
What's that?
And just, I don't know, give it initial conditions. Where it is.
Well, we did, though. I said that the velocity was 3 meters per second, so hopefully it works out. I don't know. We'll find out. So 1/2 times 4 kilograms times what? I said 3 meters per second was our initial speed. We got to square that thing. So that minus 1/2 mv naught squared, what's that give us? Well, minus 1.5. So this tells me that what? Minus 1/2 mv naught squared equals to what? Minus 1.5 joules. Minus what? Oh, maybe I'm wrong. Maybe. Oh, never mind. Oh, I'm sorry. Hold on a second. What have I done?
We don't know.
Excuse me. Excuse me. What have I done here? Come on, guys. Don't let me do this. Flippity floppity. No. Look. VF, we don't know. Right? V naught, we know. I've juxtaposed. So I'm supposed to have a minus on this and a plus on this, and this was the thing I don't know. All right? So this gives me 1/2 mvf squared. Sorry, guys. Equals to minus 1.5 plus, hopefully this wins, 1/2, which is what, 2? That's 2 kilograms times, apparently times 9 meters squared per second squared. Well, hooray. It's going to be okay. It's all going to be okay. We're going to get a positive energy. A positive kinetic energy. You can have negative potential energy. That's okay. Negative kinetic energy, on the other hand, not okay. So, guys, what do we got? 18 minus 1.5. So it probably didn't slow down much, actually, because 18 was its initial kinetic energy, apparently, if I haven't messed that up. Do I have confirmation? So I've got 1/2 mvf squared is equal to, if my calculations are correct here, 16.5 joules. All right. And then what? Solve for VF, right? So VF squared is equal to 2 times 16.5, which I think is 33 joules, divided by m, which is 4 kilograms. My 10-year-old doesn't like this kind of number. He says that this is an off-brand number because it's like not finished, you know, like it's only real once you make it into a decimal. So he says this is not a real number, basically, is what he says. Tell my son he's a nerd. I will do that, thank you. That's funny. So I get the square root of 8.25 meters squared per second squared. Somehow adding "sir" onto that makes it funnier. I don't know why. You know? Anyway, so I get 2.872 meters per second as my final velocity in this situation. All right? Don't get lost in the details. Let me summarize what we just did. The work energy theorem says the work done by the net force is equal to the change in the kinetic energy. In the context of one-dimensional motion, if we have a plot of force versus position, we can calculate the work done by just direct computation of areas, right? So there's that. That's pretty much it. Let me take a stab at another one of your mastering kind of problems here. Let's see here. Here's the pulley problem. You got two paint buckets connected by a lightweight. This is problem 7.51. Example 3. 7.51 basically. This is what we're talking about. So you got two paint buckets connected by a lightweight rope. Let me draw a picture here. Pulley. All right, so we got one guy down here, like this, 4 kilograms for me, and we got another one up here, 12 kilograms. All right, this distance here is my real height of 2 meters. So it says a system of two paint buckets connected by a lightweight rope is released from rest with the 12 kilogram bucket 2 meters above the floor. It says use the principle of conservation of energy to find the speed with which the bucket strikes the floor, ignore friction and the mass of the pulley. All right? So how do you do this? So what I usually do in this kind of situation is I invent, you don't want to think about, you really don't want to think about the starting or the ending. You want to think about like a middle, what's the word? In between, yeah, in between case. So you want to look at setting up the formulas, at least I do, like something like this, all right? So this distance here, we could call y1, and this distance here we could call y2, right? So what can you tell me about, and you know, this is m1, this is m2 for the sake of ignoring my numbers. So that would be somewhere in between. But what is always the case about y1 and y2? So like here, we've got y1 equals to 0 and y2 equals to what? 2 meters, right? So that's the starting point. The ending point is what? So we end at y1 equals to 2 meters, y2 equals to, my bad, other way around. y1 equals to, no, I got it. y2 equal to what? 0. What is the case at every step in between? That's right. y1 plus y2 has to be equal to 2 meters. What that expresses is that the rope does not stretch. All right? And if you wanted to get into the kinematics of it, like the acceleration of the buckets and such, which I think would be constant here, then that's an important consideration. Anyway, so let's get to it. What's the total mechanical energy? Total mechanical energy is, you got yourself 1/2 m v1 squared plus 1/2 m v2 squared, right? That's the total mechanical energy in the kinetic sense, right? Kinetic energy of the first mass, kinetic energy of the second mass. We're told that the pulley is massless, which means that there's no kinetic energy bound up in the rotation of the pulley itself. At the end of this course, a little bit later, we'll actually talk about moments of inertia, so the actual spinning of the pulley itself will also have an energy, like a yo-yo. But not yet. So massless pulley, massless rope. What's that? Yeah. Okay, so then what? Plus the potential energy, which is m1 g y1 plus m2 g y2. That is the energy at every single possible motion between the starting and the ending. All right? But we can calculate the total mechanical energy at the start of the motion, because what are we told? It's released from rest, right? So at the start, let's say E naught, we have, we just have, we just have potential energy. So what's the initial energy? Y1 is 0, right? So we just have m2g times, 2 meters, right? That's the initial energy. Do we agree? Disagree? Do you guys see what I'm doing? There's no kinetic energy because it starts at rest. How about the end? The final energy, what's the final energy? The final energy is 1/2, that was supposed to be m1 and m2 obviously. So 1/2 m1 v1 squared plus 1/2 m2 v2 squared, right? Plus what? So at the end, we have what? We have y2 is 0, but y1 is 2, right? So we'd have m1 g times 2 meters. What does this tell me, by the way? Among other things, this tells me that v1 is equal to v2. That's not quite true. What does it actually tell me? I mean, that's a lie.
Well, they're opposites.
They're what?
They're opposites.
They're opposites, right. So v1 is minus v2, but it is true that v1 squared is equal to v2 squared, because that minus gets eaten up in the squaring, which, long story short, we might as well just say v1f equals to v2f equals to let's just call it the final velocity, right? Again, I have to put a minus there, technically speaking. Fine. All right, so getting to the point, finally. Let's solve this. We've got m2 g times 2 meters minus m1g times 2 meters is equal to 1/2 m1 vf squared plus 1/2 m2 vf squared. Which, let's clean this up a bit. We've got vf squared is actually equal to what? It's equal to m2 minus m1 minus m1 times g, right? Times my 2 meters, which I factored out. And then I'm dividing by, I might as well multiply by 2, so I'll put another 2 up here. And then that gives me m1 plus m2, I believe. Yeah. Using algebra. So VF is equal to square root of 2 times my mass 2 was 12 kilograms. So I got 12 minus, what was the other, 4 kilograms for me, divided by 12 plus 4, which is 16. And then I've got times 9.8. And then I've got times my 2 meters. But I'm just going to leave that as a 2 and just say the units are meters over seconds outside this root. Whatever that is. Again, don't get lost in the details. All we're saying here is energy is conserved, and we need to write the total mechanical energy is the sum of the kinetic plus the potential. And we need to recognize what we're given at the start of the problem and at the end of the problem. And if we do that, and we're careful with, algebra, we should get it okay. 8, 2. So if I haven't made a mistake, inside the square root we had 19.6. And that gives me a 4.43. I guess 4.427 meters per second is what I get for my numbers. Let me just double check my answer over here. Hooray! So it's got 4.4 meters per second for my particular set of numbers. You've got different numbers, but you can set it up the same way I did, right? In fact, I think I just foolishly derived a formula you can just use to solve this problem. Oops. I shouldn't do that. Well, here I'm torn. I'm torn. On the one hand, if I work the problem in such a way that I find an elegant and nice formula in terms of the parameters of the problem, this is actually how you should solve physics problems. You should not put numbers in. Putting numbers in before the end is not smart. Like, it is usually better to work with letters, get to the end, and then put the numbers in at like the very end, as opposed to putting the numbers in as soon as you can, and then being lost in the digits. It's much easier for me to get partial credit if you make an arithmetic mistake going from here to here, as opposed to making an arithmetic mistake somewhere in the midst of equations. And you can never tell me what you equate. You never no one ever is like, I'm using conservation of energy, blah, 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 blah. Like, no one writes this sentence. You just write numbers, and like, I'm supposed to somehow read your mind. But I try to, but I can't always, So anyway, I'm just saying keeping things symbolic is actually like a good practice to get into. Yeah.
So in this example, instead of writing 2 meters all throughout it, would we just put a Y?
Oh yeah. We could have put called that H or something. That would have been better. If I was to be true to my method, yeah, I should just call this particular thing H and say and then that would have, instead of putting a 2 meters here, we'd have had an H as the answer. And so if I had asked the question differently, right? If I'd said instead the 12 kilogram bucket was at H equals to 3 meters, the same physical setup would give me the answer for 3 meters, right? If I solve it symbolically, I've solved it not just for the one situation that you're given, but for all possible contingent situations, which is like a better way to work out things.
So what you're saying is do our best to find formula or derive.
Yeah, I think deriving formula is a good. Now, we're not all ready for that. Like, sometimes you just have to put numbers in because that's what is comfortable for you, and that's fine. I'm not saying you can't do that. I'm just saying that it's better to not. But I slip in and out of it myself, all right? So, yeah.
What
Yep.
is that formula by chance of the timeless equation?
I don't know. I don't think it's anything in particular. It's specific to this particular, situation here. But another example I should show you guys today before we're out of time here, if I can find my eraser. Oh, here it is. So one of the things that I told you guys that if you have a static force, right? A static force field, a force which does not depend on time, it matters not your choice of trajectory for a given path. Like if you connect one point to another, if the force itself does not depend on time, it doesn't matter how fast you go on the path that connects 2 points. Like, it's going to be the same work done. Man, I put a sticky note in here, and I'm not finding it. A second, guys. You guys don't mind if I go 5 minutes over, right?
Unfortunately, my phone has died, so I need to get back to my dorm as soon as possible. I don't even know how I'm going to get into my dorm.
Oh, wait a minute. This is news. So your phone just died. I have good news. We still have 15 minutes left.
I think my watch died, but I have to check back to my dorm.
All right, so the force is equal to
What about all my little brothers? I want to hear my
minus alpha xy squared. And in your book, so they use like this J-hat thing, right? But for us, civilized people, that means that the force is 0 minus alpha xy squared, all right? So this would be the force. And they might ask you to find the work done to go from like here to here, all right, where this point is 0, 0, and this point might be, I don't know, 2, 3 or something in meters. And so the question then is, how do you, first of all, it's not a conservative force, all right? It's not a conservative force, so we can't do the potential energy thing. How do you actually calculate the work done? So for a problem like this, you need to parameterize a line segment. A lot of problems in your homework, basically you need to know how to parameterize a line segment. So how do you do that? A simple trick is this. R of t is p plus t times q minus p. What this does for you is it starts at p at time 0, and it puts you at point q at time 1. So this is a simple formula to parameterize the line segment that goes from point P to point Q, this being t equals to 1, this being t equals to 0. Putting that into practice for this example, my parameterization for this line segment here is 0, 0 plus t times parentheses like 2, 3 minus 0, 0, which is very silly here. That's just 2t, 3t. Long story short, x is equal to 2t, y is equal to 3t, for 0 less than or equal to t less than or equal to 1. That is how you could set up the work integral for this force field, all right? So we'll do one of these in detail next class, but I just wanted to give you that, because there's about like 5 parts in your homework which basically are doing this, all right? So the point is, there are problems in your homework where you're going to have to make up formulas for the path to calculate the work done. That's how you can do it. Yep. Thanks, guys.